We'll wait a few minutes more. We start maximum 35, okay? Good morning to everyone. So we start this first session about heavy flavor and high energy. The first speaker is Laura Moreno Valero, and she will talk about soft glue resummation for the production of 4 top quarks at the LHC. You have 20 plus 5, so the floor is yours. You can start.
Okay, thanks. First of all, I'd like to thank the organizers for the invitation to the workshop and also for the possibility to present our work here. So, as you said, I will talk today about improving theoretical predictions via soft glue resummation in the absolute mass threshold for the production of 4 top quarks at the LHC, which has been done in collaboration with Melissa van Vickveld and Anna Kulesha. So the first question is why the 4 top? Why is the 4 top relevant? The top quark is the heaviest standard model particle, and so it plays a special role in the model and beyond. If we take a look at some of the diagrams contributing to this process, like these ones here, we have that the Higgs couples to the top quark. So we have that this process is sensitive to the Yukawa coupling. It also contributes to beyond the standard model background, and the cross-section can receive potential contributions from BSM processes as well. So it is sensitive to new physics. In the context of effective theories, we have that this process can set some constraints on, for example, the 4 fermion operator, if I find now here. And the 4 top production is actually one of the rarest standard model processes accessible now at the LHC, since it has 4 colored massive particles in the final state, namely the 4 tops. So, yeah. It's interesting to consider this process. Here we show some of the diagrams contributing at leading order. We have 2 different channels contributing at this order, the quark-antiquark and the gluon-gluon channel. Even though it has a very small cross-section of the order of femtobarns, as we will see in the results, this process has already been measured at the LHC by both the ATLAS and the CMS collaborations. We can see the measurement here at the bottom right of this plot. And even more, it has already been observed in some of the production channels. So we are talking here about the multileptonic final state, in particular the 2 leptons with the same electric charge or more than 3 leptons in the final state, where significances over 5 sigma have been obtained by each collaboration. We show here the reported or the observed significances by CMS and ATLAS, and also the reported cross-section for these production channels, where we can see how they compare against the standard model prediction finding an excess. There is also evidence of this process in other production channels, so in the 1 lepton final state or in the 2 leptons with opposite charge. And we can see, for example, for the ATLAS analysis, how there is an excess of 2 standard deviations with respect to the standard model prediction. Regarding the status of theoretical predictions, we have the next to leading order QCD results were obtained or calculated some time ago. But at leading order, for example, we do not only have pure QCD diagrams, but also diagrams involving electroweak interactions. And so next to leading order results involving both QCD and electroweak corrections have also been obtained, as well as combined results including parton showers. But next to leading order results are not at reach for such a process, so we have to look for alternative ways in order to increase the precision of our calculations, which is precisely the goal of this talk. So we will extend this precision of theoretical predictions beyond next to leading order for the four-top production by taking into account the effects of soft gluon emission. So for that, we start by taking a look at the cross-section. We can expand it perturbatively in powers of alpha s or of the coupling constant. And at every order, these coefficients here will contain some logarithmic structures of this form, which originate from multiple gluon emissions. There are certain corners of the phase space, so when we approach certain kinematical configurations, where these logarithmic terms will become very large. And this is, for example, the case where we consider additional gluons to be soft. There is one particular corner of the phase space that we're interested in, and this is the one that we refer to as the absolute mass threshold, in which the idea behind it is that the energy from the initial state is just enough to produce the final four tops almost at rest. That means that any other additional radiation, such as gluons, must be very low energetic, or as we call it, soft. And in this case, we have that this condition here is satisfied. And so it becomes clear that these logarithmic terms become very large, and they might spoil the predictive power of this perturbative series. What one has to do then is take all these terms into account and go to all orders, which is achieved by performing resummation. We have seen some examples of threshold resummation in this talk, I think yesterday. And so there are different approaches to threshold resummation, for example, the soft collinear effective theory approach, or the one that we will be working in this case, the direct QCD and Mellin space approach. But now let's take a look at the general picture. So we start with the cross-section, and by means of the factorization principles, we have that we can write the cross-section as a convolution of different contributions. So here we have the hard amplitude matrix, or a piece containing the soft emission information, as well as some functions containing information about collinear emission from the massless legs, so both for the initial state and for the final state. And these large logarithms from before will be contained in some of these functions here. In direct QCD, so in the approach that we're taking, factorization is based on resummation is based on the factorization of both the matrix element and the phase space, and this factorization takes place when we work in the so-called Mellin space. If we now take the logs from before, so these forms of logarithms, and we perform a Mellin transform to them, we see that they transform into logarithms of the Mellin moment n. And in this case, so in the Mellin space, we have that the cross-section will no longer be a convolution of the different contributions, but a simple product of these functions. This resummation procedure will then lead to an exponentiation of these enhanced logarithms near threshold, such that in the simplified case of a color singlet, the cross-section will look like this, where now we have all these enhanced logs contained in the exponential and therefore resummed. Each of these functions here in the exponential, we saw also these yesterday, but we have that these functions will each generate several powers of logs. And for example, the first function, the maximum power of log that it will generate will look like this, and we refer to it as the leading logarithmic contribution. The second function will also generate certain powers of logs, and the maximum power of log that it will generate will look like this, and we refer to it as the next to leading logarithmic contribution, and so on. And then in this prefactor here, we gather finite contributions. So if we want to perform resummation at a certain accuracy, we then have to take into account the corresponding contributions. Let's say we want to perform resummation at next to leading log accuracy, we then have to take these two terms in the exponential into account. That was quite general, but now let's take a look at what happens for the four-top production. So here we present the resummed partonic cross-section in Mellin space, where the first thing that we see is that everything is factorized, as expected in Mellin space. And now taking a look at each contribution separately, we start with these delta functions here, which are the incoming jet functions, and they gather the contributions from soft collinear emission from the incoming legs. These are universal functions, and they only depend on the kind of parton that we have in the initial state, so whether we have a quark or a gluon. We then have this trace here with a hard function for the hard dynamics and the soft function, both of them being process dependent, and therefore they need to be calculated. The zeroth ordered hard function, so the lowest order of this function, is obtained by considering the Born amplitudes of the process, and the soft function can be expressed in terms of the evolution functions of these soft functions, so these functions u, and also the boundary condition. The evolution of the soft function is driven by the soft anomalous dimension matrix. I will talk about it a bit more in detail in the next slide, but there's also a talk in the next session. And yeah, so it is all this whole green block, this whole soft function that tells us about soft wide-angle emission. Since we are working with a process involving several colored particles, actually all of them are colored particles, we then have that these functions here will be matrices in color space. So we move now to the soft anomalous dimension matrix. We can expand it perturbatively in powers of alpha s, like here. And if we want to perform resummation at next to leading log accuracy, only the one loop soft anomalous dimension matrix is required, which is this term here. It is a matrix in color space, so we need a color basis to define it. And the first step is to know the dimension of the color basis. So for that, we take a look at the color structure, both in the initial and final state for each channel. And we find that for the quark-antiquark channel, we require a 6-dimensional color space, whereas for the gluon-gluon channel, we require a 14-dimensional color space. Now, to obtain predictions for the cross-section, we move to another color space, or to a color space, in which the soft anomalous dimension matrix is diagonal at threshold, such that the soft piece, which, if we remember, it was the product of these three matrices, instead of containing path-ordered exponentials, then it reduces to a simple exponential. So this will be the next task, to find the suitable color basis for each channel in which the soft anomalous dimension matrix is diagonal at threshold. So we start with the quark-antiquark channel. We have a 6-dimensional color space here, which is the basis proposed in this paper. We compute the 6 times 6 soft anomalous dimension matrix with full kinematics. And now we apply the absolute mass threshold limit, so we bring these 4 tops almost to rest. And we find that this matrix is diagonal at threshold. So far, so good. We already have a diagonal matrix at threshold. We can apply the expressions from the previous slide. Now we move to the gluon-gluon channel. Here we have a 14-dimensional color space. And so we take, once more, the basis proposed in this paper. We compute the 14 times 14 soft anomalous dimension matrix with full kinematics. It does not fit completely here because of the large dimensions, but you have some of the elements here. We then apply the absolute mass threshold limit, and we find that this matrix is not diagonal at threshold. So what we do is we propose an alternative basis written in terms of the old basis vectors, for which now the soft anomalous dimension matrix is diagonal at threshold. Now we have the suitable basis and the soft anomalous dimension matrix diagonal at threshold for both channels. So we go back to the original slide, and we present the results here for NC equal 3. Where we can actually see that the elements of twice the real part of the soft anomalous dimension matrix with a minus sign correspond to the quadratic Casimir invariance of the corresponding representations for each channel. So this constitutes a check to our calculations. With the knowledge of the soft anomalous dimension matrix at one loop, we can perform our resummation at next to leading log accuracy, but we can also extend the accuracy of our predictions by taking into account these first-order contributions to the hard function and to the boundary condition of the soft function. So these two alpha s contributions here. But let's go step by step. So first we consider the next to leading log, the exponential functions at next to leading log, and we consider also only the 0th order terms of the hard and the soft functions, such that the trace looks like this. With this, we'll be getting predictions for the cross-section at next to leading log accuracy, and these H0 term, so the 0th ordered hard function, is obtained by considering the Born phase space integration of the color stripped amplitudes, whereas this S0 term is obtained by considering the trace of the color basis vectors. So now we go this step further with accuracy and consider also these first order contributions to the hard and the soft function. This H1, so the first order hard function, is obtained by considering one loop virtual corrections and also constant terms from collinear enhancements, whereas this S1 function is obtained by considering constant terms to the soft function. So now we take once more the exponential functions at next to leading log, but the product of the hard and the soft function up to order alpha s. So we have this trace here, and then we call the resulting accuracy next to leading log prime. This is important to keep in mind because this will be the notation used throughout the results. So this prime includes these non-logarithmic order alpha s contributions. The leading order amplitudes, so the Born amplitudes, and also these one loop virtual corrections, have been numerically extracted from AMC at NLO code where we implemented these color pieces that we discussed in the previous slides. And yeah, so with that, we can obtain predictions for the resumed hadronic cross-section by taking into account the partonic resumed cross-section, which we've just discussed, and also the Parton distribution functions in Mellin space. We then perform an inverse Mellin transform to go back to the original space. And with that, we are taking into account these enhanced logarithms near threshold. But we know that the cross-section receives also potential contributions from other regions as well. So in order to get a proper result, what we have to do is to combine both fixed order calculations and the resumed cross-sections. There is an overlap between both of them. So what we do is we take the resumed cross-section, we expand it up to the order that we want to combine the result with. This is precisely the common piece between both of them. Then we subtract them from the resumed cross-section, and then we can combine it with a fixed order calculation. And with that, we'll be getting matched results. So in particular, in our case, next to leading log, or next to leading log prime, depending on what we consider, matched to next to leading order. So now we're ready for the results. And first, we want to see how well the next to leading log, so the resumed cross-section expanded up to next to leading order approximates the next to leading order where the quark-gluon channel has been subtracted. At leading order, we have seen we have two different channels, quark-antiquark and gluon-gluon channel, but no quark-gluon. And resummation is performed on top of channels which already appear at leading order. So in order to make a comparison between the expansion of the resumed cross-section with a fixed order calculation, we then have to subtract the quark-gluon channel from the fixed order. And yeah, well, this subtraction is only performed here, but later when we talk about match results and full fixed order calculations, the quark-gluon channel will be included. So we get these results here, where we can see how the resumed cross-section expanded up to next to leading order is a good approximation of the next to leading order where the quark-gluon channel has been subtracted. And that tells us that the dominant part of the next to leading order corrections is captured by soft-gluon radiation. And also, we can see how the scale dependence of this next to leading order without the quark-gluon channel is well captured into our expansion. Now we bring these results to the background, and we consider now the scale dependence of the cross-section for fixed order calculations and matched results. We will be considering next to leading order with only QCD corrections, and also next to leading order including both QCD and electroweak corrections, the last ones up to order alpha squared. We set the renormalization and the factorization scale equal, and we vary them simultaneously around the central value of the time set of mass. And we consider this PDF set here and a center of mass energy of 13 TeVs. We start then by taking a look at the fixed order with only QCD corrections or with only QCD contributions, so leading order QCD and next to leading order QCD. We then include the effects of soft-gluon emission at next to leading log accuracy by including these exponentials at next to leading log. We then improve or upgrade to next to leading log prime by including these non-logarithmic order alpha S contributions. And then finally, we match it to the next to leading order QCD plus electroweak, arriving to our final prediction here in purple. And what we see is that resummation has a great impact on the scale dependence in the sense that it is significantly reduced and therefore improved when including these resummation effects. The K factors are also quite sizable, so if we take a look at the next to leading order QCD plus electroweak, when looking at the numbers, it will be more clear. But if we take a look at the central value for this cross-section, to our final prediction, there is an increase of 15%. And one can also see that the non-logarithmic order alpha S contributions are quite relevant. And you might wonder how coincidental this present result here is, given the fact that we are setting the renormalization and the factorization scale equal. So to answer that, what we consider is as an independent variation of both scales. So we vary them independently by considering the 7-point scale variation method. And we arrive to these results here, where we show the fixed order calculations and resummation improved results. Now, this error bar includes the theoretical uncertainty due to scale variation following the 7-point scale variation method. And we can indeed see that there is a strong reduction or a significant reduction of the scale uncertainty when including these resummation effects. And by looking at the numbers, one can say that this is actually by more than a factor of 2. Here we can see the key factors with the 15% increase that I mentioned before, and also that so these percentages here only include the scale variation, but one can consider also the associated PDF error to the fixed order calculations, which we found to be around 7%, and so we see how the scale uncertainty dominates over the PDF error. I'm going to skip that because of time. And we can perform a similar study, but now considering a center of mass energy of 13.6 TeVs. And so we show here once more fixed order calculations and resummation improved results. So if we consider a larger center of mass energy, we expect larger cross sections. And this is indeed what we see when we compare with the 13 TeVs. But the behavior remains the same. So there is also an increase of or a reduction, more or less, more better said, of the scale uncertainty when including these resummation effects. And one can take a look at the numbers here in the table and see that this reduction is again by more than a factor of 2. The key factors are more or less the same size as before. Then one can consider varying or considering different values for the top mass within the range of 170 and 175 GeVs. And we show here the fixed order calculation and also the resummation improved cross-section, where we actually see that the top mass dependence is not modified by the inclusion of soft glow emission effects. So now arriving to the summary or to the conclusions, we have extended the precision of our theoretical predictions beyond next to leading order for the production of 4 top quarks by performing resummation at next to leading log accuracy, including on top non-logarithmic order alpha S contributions. This is the first time that soft glow emission was resummation was performed for a process involving 6 colored legs, external legs. And throughout this presentation, we have seen how we have gotten to our final prediction, which we show here, the next to leading order, if I can find, the next to leading order QCD plus electroweak matches next to leading log prime, where we have found a significant reduction of the scale uncertainty compared to fixed order calculations. And now we can actually see how this compares to the results reported by Atlas and CMS. So it's a bit difficult to see maybe, but we started from this line here, with the prediction at next to leading order QCD plus electroweak with an error band dominated by scale uncertainty. And then by including the effects of soft glow emission, we have moved to this purple part with the central value here with a larger central value, but also a much reduced scale uncertainty. And now the question is what follows? So there are many more things that one could do, so many more steps to be taken. For instance, all these calculations and techniques developed during this project can be applied to other processes as well, involving several colored particles. This is precisely the case of the top pair, bottom pair, so TT bar, BB bar, when we consider the bottom quark to be massive. So in this case, we have once more 4 colored massive particles in the final state. One can also consider invariant mass threshold resummation instead of absolute mass threshold resummation. The idea then is that behind this other kind of resummation is that threshold resummation is that the energy from the initial state is just enough to produce the final 4 tops with a certain kinematical configuration. And in this case, one would have to, for example, compute the soft autonomous dimension matrix at every phase space point with a full kinematics, and then numerically diagonalize it. But one can also, or it makes more sense to obtain differential distributions in this threshold. But as I said, there are many more steps to be taken. One can consider also a different kinematics, or one can extend the accuracy of resummation. But this will be all for today's talk. So thank you for your attention.
So thanks, Laura, for this very clear presentation. The floor is opened up for questions. Do we have questions? Yes, please. There.
I actually have 2 questions. The first one is the top width playing any role in your analysis, or do you consider stable tops?
No, so we consider stable tops, so no decay.
And second question, what heavy quark mass scheme are you using for the top quark? Is it Paul mass or MS bar?
MS bar, actually, yeah. Yeah, MS bar.
Okay, thanks.
So if you have stable tops, then you have bound states below threshold, right?
Yeah.
Other questions? Actually, I have one fast question. It's not just a naive curiosity. You mentioned that you do a precision study about uncertainty coming also from scale variations and from PDFs, no? Would it be possible to give an estimation of the error committed when you do the matching procedure? Can you gauge this, or maybe changing the matching procedure, pass from an additive to a multiplicative one? Can it allow us to better gauge what is the effect of the matching procedure, the impact?
We haven't done that, so I'm not able to give an estimation. But yeah, one could maybe consider some other matching, but we are just using this expression here, so yeah, I'm not able to, this expression here, so I'm not able to give an estimation.
Yes. Okay, thanks. Other questions? So if there are no questions, let's thanks again, Laura. And let's move to the next speaker, who is online. So we need to connect with the Google Meet stuff.
Do it now and then. So now we try. We have some problem of connection with this person, but if the problem persists, I would ask you to switch before so that we can solve it later. Okay. Let's try. Alexei is upstairs to check things from abroad, from there. So Alexei has sent a Zoom link. Can you check your email? Let's see if this guy is on Zoom. Otherwise. Okay, let's do like this. Federico, if you can come before, then during the coffee break, we try to fix this a bit better, if we can. Okay? And yeah. No, the opposite way. Switch the spin, yes. Fantastic. Ripani.
Prova? Sì.
It's Ripani. This can be.
Ok.
And I would like all speakers of next session to upload their talks, please. I see there is someone which is not. Javier is here. Is it there? Okay. Now we start with Federico.
E questo è full, diciamo è il nome del...
So what is the document?
Seminario, quello lì.
Full top.
Sì. questo.
Okay, yeah, you put it like this. Can you put it full screen? Yeah. Full top. Okay, then I go on right hand side. Okay, that one. Good. And then I put full screen. Okay, so we'll try to fix online talks later. Who's going to chair? You?
Okay, yes. The next speaker is Federico Ripani, and he will present full top core mass dependence in diphoton production at NNLO in QCD. The floor is yours.
Okay, good morning. We did fixed order computation, so we relied on the factorization theorem and didn't consider next to leading power corrections. So we computed the next to leading order in QCD cross-section for diphoton production at LHC, retaining the full top quark mass dependence. This is the outline of the talk. So after a brief introduction, I will talk about the different terms we considered, so the double real, the real virtual, and in some more detail, the double virtual. And then I will show you the phenomenological study, in particular the invariant mass distribution. So why study diphoton? This is an irreducible background to the cleanest X decay channel. In this channel, the signal is very tiny, is very small compared with respect to the background. So it is important to have an accurate theoretical prediction of the background as well. It is an experimentally clean final state, and so it is a good test for the standard model. It is also a good channel for searches of new physics. Why keep computing corrections to this process? So if we look at the values of the total fiducial cross-sections, we can see that both theoretical and experimental uncertainties are of the order of 8%. Nevertheless, preliminary studies tell us that experimental uncertainty will decrease up to 1%. So the phenomenological importance of diphoton push us to improve the theoretical accuracy as well. So if you want to compute the diphoton cross-section, you have to download one of these programs. One of these is Sherpa, which implement an next to leading order QCD correction plus extra real radiation, and an emulation of the resummation with Parton shower. The other two programs are NLO JET and 2-gamma NLO, which both implement fixed order massless next to leading order QCD correction, the first with antenna subtraction, the second with QT subtraction. Further corrections have been computed, not all of them included in phenomenological studies. For example, all the elements for n-cube LO have been considered, also the top quark effects in the gluon fusion channel. Electroweak and QED corrections are known at next to leading order, as well as QT resummation up to n-cube leading logarithms accuracy. We considered for the first time next to leading order corrections retaining the full top the full top quark mass dependence. So the scheme we computed the correction with is a fixed order scheme with QT subtraction. All the massless terms are known. What we did is to add the contribution coming from the top quark. As we see, the top quark starts to contribute at next to leading order in different ways depending on the channel we are considering. For example, in the quark-antiquark annihilation channel there are present the double real, the real virtual, and the double virtual contribution. So let's start from the simple pieces. So on the right, I'll show you the double real contribution to the invariant mass distribution. On the left, the real virtual, the black line, the real virtual contribution. The amplitudes for these processes were known. Nevertheless, we computed them independently and checked the results with the program OpenLoops finding agreement. Let's go to the bottleneck ingredient before unknown, which is the two-loop double virtual in quark-antiquark annihilation channel. So we use the usual steps for scattering amplitudes computations, diagrams generated with fine arts, symbolic computations done with form, and so on. This amplitude can be projected on 4 independent Lorentz tensor structure and dig up to 4 scalar form factors, which are linear combinations of thousands of Feynman integrals that we have to compute. In this case, the Feynman integrals can be grouped in 3 different topologies, 2 planar, 1 non-planar, as we can see from the representatives diagrams on the top of the slide. So we reduce these Feynman integrals to master integrals through solution of integration by parts identities. Using the program Kira. This reduction, it was not this case, but sometimes is a bottleneck for the computation of scattering amplitudes. We adopted the differential equation method for the computation of this basis of master integrals. In particular, we found analytical boundary conditions and evolve in all the phase space region semi-analytically with an approach based on generalized power series expansion. So we computed the master integrals in a grid of points, and after an interpolation we have a numerical routine which allows us to perform phenomenological studies. So let's enter in some details what was the master computations. So this amplitude involve 42 master integrals. Some of them are already known, for the planar and the 3-point non-planar functions. Instead, the 4-point non-planar functions are in some sense new, and in this work we have computed them for the first time as a generalized power series expansion. So what this method is about, let's start from the differential equation master integrals satisfy with respect to a line parameter x of a curve along the kinematical variable space. Also some boundary conditions have to be known. This method relies on the fact that every Feynman integral can be expanded in the vicinity of a point, regular or singular, as a finite sum of generalized power series times some logarithms raised to some finite powers. The unknown coefficients c and the rational exponents r can be determined starting from the differential equation and from the matching with the previous expansion. or with the boundary condition. So, in particular, for the amplitude we considered, we generated two systems of differential equation, one for the planar topology, one for the non-planar topology. Let me comment on this. In general, generalized power series works for every basis of master integrals. Nevertheless, a good choice of basis has to be done in order to speed up the algorithm. This is sometimes a bottleneck for a completely algorithmic approach to scattering amplitude computation. We found the canonical basis for the planar topology, and for the non-planar topology we have found a canonical subsystem and a residual system which is related to the non-planar top sector, which involve elliptic functions. The canonical basis allowed us to find simple analytical boundary conditions in the origin of the kinematical variables region. As I said, we evolved in all the phase space through one-dimensional generalized power expansion series using the program diffexp. So we did a grid in which we evaluated our master integrals in covering the physical region of interest. We using the program diffexp and checked the results with the other programs available, for example, Seaside and Inflow, finding a good agreement up to 200 digits. I show you the plot of the non-planar master integrals as function of center of mass energy at fixed scattering angle. We evaluated the master integrals in a grid of points covering the physical kinematic variable space of interest. After an interpolation between these points, we have a fast numerical routine to evaluate the form factors and their function, which allows us to perform phenomenological studies. So let me observe that top quark correction introduce a scale dependence from the center of mass energy, as we can see from the bulk structure in the plot shown. So now we have all the ingredients, and the plot shows the ratios of each singular contribution with respect to the total massless next to leading order cross section. As we can see, the red line, which is the double virtual term in gluon fusion channel, contributes as the same size of the black line, which is the double virtual quark-anti-quark annihilation channel contribution. So they contribute as the same size, roughly, around the top quark mass threshold. Instead, in the region around 800 GeV, the gluon fusion channel is definitely dominant. At high energy, the quark-anti-quark annihilation channel is dominant and represents a negative contribution to the cross section. If we sum all these pieces together, we obtain the total mass invariant distribution that we computed plugging in these corrections inside the program to Gamma law, which implements Atlas fiducial cuts, the standard 7 points uncertainty estimation, and the smooth isolation cone, which allows us to don't consider the fragmented photons. So as we can see from the plot below, which is the ratio between the total cross-section with the top quark mass dependence and the massless cross-section, we can see that massive corrections represent a correction of the order of 1%, which is of the order of the future experimental uncertainty reached by Atlas analysis. So, summarizing, we computed the cross-section at fixed order up to next to leading order, retaining the full top quark mass dependence. In particular, we focused on the double virtual term in quark-anti-quark annihilation channel, which was unknown and involved the computation of new master integrals. At the end, we found that the total massive correction represents a correction of the order of 1%. Which is compatible with the future experimental uncertainty. What are the outlooks? We have in plan to include in our prediction all the terms that can be of the same order. In particular, the n-cube corrections in quark fusion channel, with massless and massive corrections, as well as resummation that can carry important contributions not only in the non-perturbative region, but also in the perturbative region. Thank you for your attention.
Thanks for this nice presentation. Do we have questions from the audience? I see there a question.
Hello. Thank you for the nice talk. So maybe I missed something. So you use, you computed the double virtual correction by semi-analytical method, and you in like QT slicing method to combine double real and so on, or which subtraction scheme do you use?
The subtraction scheme? Sorry.
Yes, for real and real virtual contribution.
Okay. So the scheme is the QT subtraction scheme, but all the IR divergences comes only from the massless parts. So the massive contributions doesn't carry IR divergences, so they are IR free.
Okay. I see.
So we needed only for the massive terms. We needed only the UV renormalization, and after that everything is finite, and you can plug in as we done in the program to Gamma law and compute the correction without additional.
Okay, I see. So because it's massive, right? Okay, and so it's then it's about the massless IR things. So how about the Paul correction here? About QT Paul correction? Do you see that? Because it's still like a QT subtraction, right? Okay. Because for massless IR, you use the QT subtraction to deal with the IR divergence. So do you know the Paul correction here? It's large or like The QT power correction, yeah.
Then
QT over Q, yeah. The power correction of QT over Q. Yeah,
power corrections. Okay. And honestly, I don't know the importance of these corrections, but they have been included in this work. They have been in this work from Becker and collaborators in 21. I don't know if they included the resummation of logarithms up to n cube.
Okay, there is another question from Ignazio.
Yeah, if you go to slide 15, when you have your error, and the shape of your error is pretty weird in the sense that for very small PT, the error seems not 1%, but 1 per mil, or even less. Is that some particular things you can comment?
Okay. You mean why here is very small with respect to... of course, we can, so we introduced only these sorts of uncertainty. So let me...
May I ask something?
So let me think.
Is it a change of sign in the error, probably? No.
Yes. These bands are taken by considering scale variation.
Yeah, by considering scale variation. No, the question was why here we don't have...
According to my experience, in general, scale variation leads to a large, an increasing uncertainty with this is mass, no? No, I was thinking the PT, but in general, large mass could lead to a larger scale variation, no? Because if you do 2 times 1/2.
Honestly, I don't know why.
Okay, never mind. Sometimes it happens.
There is another question there.
Hi, a more experimental question from here. So here in the ratio you showed you have a dip around the 2 times the top core mass.
Yeah.
But in the absolute, in the cross section, will you also have such a dip?
Yeah. This is the total cross section. So you should see a little bump, but is too tiny to be seen in the plot above. So if you do the ratio between the cross section, the total cross section, retaining also these top quark corrections, and the massless cross section, you can see this bump.
But this is too tiny to be exploited for a mass determination of the top quark, for example.
It's too tiny?
Could the dip be exploited experimentally for a top quark mass determination, or is too small?
No, you cannot see it experimentally, this bump, because the uncertainty is too big now. But some preliminary studies tell us that tell us that the uncertainty will decrease, and maybe we were able to observe such.
When you mentioned that the uncertainty experimentally is, the preliminary studies show 1% is in the total cross section.
Yes, the 1% on the total. Yes, 1% on the total cross section.
Yeah. Okay. Thank you.
Other questions? So if there are no more questions, let's thanks again the speaker. And now let's have coffee break, and we reconvene at 10:50. Okay? Okay, let's restart the session. And the next speaker is Vladimir Salev, and he will present associated production of heavy quarkonia and D-meson in the high energy factorization. So let's start. Vladimir, whenever you want.
Okay, thank you. So, hello everybody.
We are hearing you.
Okay. Thank you. Yes, yes,
Okay,
yes.
good.
So let me start my talk. Sorry for some technical problem. What? Sorry, I should start?
Go on.
Yes, okay, well. So I will speak about association production of... Do you hear me?
Yes, it's perfect. Just go on.
Okay. So I will speak about association...
No, it's not perfect. Something
Oh.
Okay, now
The second track and sound. I hear myself.
he cannot hear himself?
He hears himself.
He hears himself, but we hear you well.
Wait,
Fantastic.
I'll just mute and then you won't hear yourself.
There is... yes.
Now go on.
So let me continue. Yes?
Yes.
Well, okay. This first the title of my talk with Alexei Chernyshov. It's okay?
It's all okay. Go on.
Do you hear me now?
Vladimir, go on. It's all okay.
Go on. Well. Oh.
Please speak. We hear you well. There is just delay between our response and your answers. Please speak.
Yes. Well, good. So, I will speak about factorization approach, which is used here, hadronizations model, and then we discussed single and double pattern scatter and interaction model, and about numerical methods. So here we see some description of the existing experimental data for pair production of gypsy. This is which we previously studied, and this is for this point will be presented in my talk now. So we will discuss associated production of upsilon and gypsy meson with the D meson at the LHC big experiment at the energy 70 eV. So well-known formulas from collinear pattern model, but we will do calculation in KT factorization exactly in the so-called pattern registration approach. So in our model, initial patterns of mass shell, each treated as regicide gluon and regicide quark. Such a way we can use effectively part of theory to describe hard matrix element in multi-reject kinematics limit. Then we can do calculation using this factorization formula when we know how to calculate by gauge invariant way hard coefficients. These partonic cross sections. So our model for unintegrated PDF a little differs from the well-known Kimber-Martin-Riskin-Watt approach. We take into account some additional dependence of the Sudakov factor from the variable x. Such a way, our unintegrated pattern distribution function can be used as an arbitrary x and hard scale mu. So main publication in pattern regression approach are presented here, and some words about hadronization model. First of all, it is color singlet model, as you know, the non-relativistic UCD approach, and we will this color evaporation model, exactly improved color evaporation model as was proposed by Mindbook some times ago. In this model, cross-section can be preceded as some integrals over invariant mass of the intermediate states, and parameter fq may be fitted. It is free parameter, and all quarkonium are treated like q bar q pairs below the threshold of the d bar d meson or b bar b meson in case of upsilon productions. So it is well known color evaporation model. Let me go to next transparency. These are recent publications in which color evaporation model used, for example, in our recent paper when we study pair production of gypsy in this model, and we fit the parameter of this model used all data from very small to very high energy. So to describe D-meson production, we use well-known fragmentational model, but we take into account mass effect in this case, introducing Z parameters of fragmentation like this. And of course, there is some cut on Z, which depends on the mass of the final D-mesons. So we use well-known Peterson parameterizations, and fragmentation fractions we are taken from the data obtained at the HERA collider from the Leonid Gladzelin work. Then we study our process taking account as a single parton scattering mechanism as well as double parton scattering mechanism, because we know that in these associated productions, both mechanisms should be taken into account. So in single parton scattering mechanism, master formula looks like this. In case of double parton scattering, we use pocket formula, and master formula for cross-section looks like this. In our previous study of the single and pair gypsy and pair upsilon production, we find that all data can be described when we put parameters of the color evaporation model equal 0.02, and sigma effective should be about 11 millibar. This parameter controls the contribution from the double parton scattering mechanism. Let me note that our value very close to average value obtained in many others experiment of associated production of different particles. So here we demonstrate that we can describe well inclusive production of gypsy meson and upsilon at the LHCb conditions. For we see that in fact we can describe well all data as for gypsy, as for upsilon. This plot from our previous study, when we suggest that in double parton scattering mechanism, we should use some new phenological parameter in color evaporation model, f psi psi, which is not equal to product of f psi, because in case of single parton scattering mechanism, we cannot describe separately, independently, the production of the two gypsy mesons. It can be done only in case of double parton scattering mechanism, or maybe in SPS production when we study fragmentation production of two gypsy, which fragmentate independently each other. But in our case, we introduce new parameters, and here we see a two-dimensional plot of our feed. So we find that there is some very small region of two parameters, sigma effective A and F psi psi, when this value about 0.02, and a sigma effective about 11 millibarn, and this region corresponds very good fit of all data as for single as for pair production of gypsy or upsilon. So, and obtained value as sigma effective is very close to recent measurement of the LHCb collaborations at the experiment of gypsy production in forward region. They obtained sigma effective about 30 millibarn. So our choice of sigma effective is very good in agreement with other measurement. Then to calculate production cross-sections, we should use analytical method based on the RGQCD model for Fencalc to obtain squared matrix element for process 2 particles into 4 particles. It is a very huge analytical calculations, and in fact, it is more suitable method to use numerical approach with the beginning, with the amplitude. In this case, we can use Monte Carlo KT. It can be used to calculate production cross-section in case of 2 particles to 4 particles in KT factorization approach. We prepared our unintegrated distribution functions which can be used in KT. We can take into account also the multi-pattern interaction using this Monte Carlo generator. Many thanks for Andres Hammerin for help. So, and what we see. First of all, we demonstrate that we can describe inclusive production of D meson in our model, KT factorization, with the main contribution from quark to quark, from gluon-gluon to C-bar-C annihilation process with Peterson fragmentation functions, and we well described LHCb data at the different range of rapidity from 2 to 4.5. So here we see experimental cross sections and our leading node KT factorization result obtained in our model, and we see that we will reproduce total cross sections, multiples for corresponding branching fractions, and here we find this ratio of contribution SPS to TPS is about 1 divided 10, both in case of upsilon or gypsy production associated with D meson. Next slide will be about different spectra. First of all, we studied gypsy plus D0 meson production. This is a transverse momentum spectrum of gypsy. We see two histograms. One corresponds SPS production mechanism, and second, the main contribution from double particle scattering mechanism. So here, the same for D plus meson. This is PT spectrum of the D meson, and D0 and D plus meson in this experiment of association production with gypsy and D meson, and we also obtained very good agreement with data. Of course, with some theoretical uncertainties, which controls our variation of the hardscape parameters. So here the spectrum of invariant mass upsilon plus D. We describe data at all in value of invariant mass, like in case of D0 and in case of D plus meson. So next slide about delta rapidity difference. It is interesting because in this case we have some discrepancy with the data in the boundary values of the delta Y when the difference between rapidity of gypsy and D meson very large. We cannot describe this strong decrease of experimental data. We predict value one order magnitude larger than in experiment, we have an explanation of such difference. Maybe it is some result of our hadronization model, color evaporation model. And in case of D star meson associated with gypsum, this difference also very large when the delta rapidity is large. So this is delta phi azimuthal and difference spectrum. Of course, it is flat and it is fully described by the double parton scattering mechanism as in D0, as in D plus production. So here we study upsilon plus D meson productions. Like case of gypsum, we have very good agreement with data for PT spectrum, both upsilon and D meson. Rapidity spectrum of the D meson also described well. And this is spectrum of total momentum of upsilon plus D. We have some difference between our prediction and data at very large transverse momentum of this pair, but the experimental value is large, as well as our theoretical prediction also have very large uncertainty in these regions. So in case of upsilon plus D plus, the situation is better. And next, rapidity of the pair, we also describe all region of this rapidity in both cases. Here, invariant mass spectrum, upsilon plus D0 and upsilon plus D star mesons. So, and once more, rapidity difference between upsilon and D meson. And as in the case of gypsum, we see a very interesting point from the experiment, which cannot be described in our calculation in our models. So maybe it should be studying additionally this difference. Maybe it is some mistake in experiment point, because we see very fast decrease data during very small change of the delta rapidity. It looks like not good experimentally. Well, so here that some parameter which describes transverse momentum difference, and we also can describe it. So here delta phi upsilon, delta phi azimuthal angle difference spectrum. It is flat once more, and it is demonstrate as importance of the double parton scattering mechanism. Maybe only point 1.0 in the back-to-back configuration. SPS contribute a little more, but even in this region, the PS contribution is much larger than SPS contributions. So, and our conclusions. First of all, we obtained a quite good description of associated production cross-section of gypsum and epsilon meson together with the D meson using factorization approach and color evaporation model without fitting of any free parameters. Of parameters of color evaporation model already fixed when we study inclusive production and association production of two gypsum or two upsilon. And our present predictions free from any parameters, new parameters. So we describe spectra of heavy quarkonium and D meson in inclusive mode very good. And we described associated production taking into account the following numerical value of the model parameters. We predict the ratio of the DPS and SPS contribution in this study, and we also obtained very well-known result that delta phi spectrum should be flat due to the DPS, due to the large DPS production contributions. And we obtain self-consistent descriptions for processes of pair production of GPSI, upsilon, and associated productions, as well as in our different approach, which we can find in HEP archive when we published our result for associated production GPSI plus intermediate boson, and for pair production of 2 heavy quark-anion. That's all. Thank you for attention, and I will wait when I'm finished in my second voice trace.
Okay, Maxime, thanks a lot. Some clap from.
Thank you.
Some claps from the audience. Then, any question?
I think it will be very difficult to do answer for questions because I'm continue to hear me.
Wait, let us collect question, if any.
Okay, thank you.
Okay, this time it seems that there are no questions, Maxime. Vladimir, sorry. And thanks a lot for your talk. And
okay. Thank you for invitation once more.
Okay, thanks a lot again. Bye. So.
Bye.
Now I would make a change in the program as we have another online talk. So it's probably better to let them all in a row, so that then we stop with the online talk and we'll let you speak. Okay, fine. So next speaker is Maxim Nefedov. And,
Hi. Yes.
Oh, okay. Vladimir, can you stop sharing, please? Okay. Maxime, you can upload your, you can share your slides.
Yes, I will start sharing my slides. Yes, so can you see my slides now?
Yeah, you can put them full screen probably.
Yes.
Okay, great. So
right.
Start whenever you like.
Yes. Okay. Yes. So I would like to thank the organizers for allowing me to speak via Zoom. I apologize that I wasn't able to come to Madrid this time. And I will be talking about also about quark-anion production, but in a slightly different context. This talk is essentially a combination of two talks. So the first part is based on our paper together with Jean-Philippe Landsberg and Millie Astzelik, which have recently appeared on Archive. And I will be talking about the following problem. So we will consider the total, namely the transverse momentum integrated cross section of production of heavy quark-anion. And since the heavy quark mass, charm or bottom mass, can be considered as much larger than lambda QCD, then one may think that this cross-section can be, in some factorization approach for quark-anion production, can be computed within the usual collinear parton model, because we have a hard scale. So we will consider two processes: the process of inclusive hadra production of eta C mesons, and process of inclusive, I stress the word inclusive, photoproduction of GPSI mesons. And in collinear parton model, and also in the color singlet approximation for the final, when we consider that only the color singlet heavy quark anti-quark pair pairs can hadronize into the heavy quarkonium. These two processes at leading node in collinear parton model are described by very simple partonic subprocesses, namely for eta C you have gluon plus gluon is fusing into the quark-antiquark pair with the same quantum numbers as the eta C, so one is 0 color singlet. And for gypsy photo production, you have a fusion of, at leading node in QCD, you have a fusion of a photon plus a gluon, two CC bar pair, and then you have to emit another gluon into the final state just at least to conserve color. And then the CC bar is in 3s1 singlet states. So, okay, these are very simple leading node partonic subprocesses, so we can relatively straightforwardly do the next two leading node calculation. And in this case, in the first case, it can be even done analytically in the closed form. And then the total cross-section of production of these mesons as a function of collision energy. So in the first case, in the ETC case, it will be collision energy of two protons. In the second case, in the photoproduction case, it is the collision energy of the photon and proton. So in both cases, the total hadronic cross-section is a convolution of some hard scattering coefficient, which I always call sigma hat, with in the first case with two proton PDFs, and in the case of inclusive gypsy photo production, there is only one proton PDF because there is only one proton. So, and this convolution is actually in terms of only one variable, which is related to the partonic center of mass energy in the partonic subprocess. So the center of mass energy of collision of these two gluons in the first case, or of photon with gluon in the second case. And okay, so we can do this next to leading node calculation in collinear parton model, and what do we find? We find that, okay, at low collision energies, when let's say when we are much less, when we are comparable with the mass of the bound state, the next to leading node the calculation behaves as expected. So the scale variation band of it is actually decreasing, but for eta C hadra production, it happens after one TeV roughly, and for gypsy photo production, it is even more dramatic. It happens after 20 GeV, as you see. The scale variation band suddenly explodes. So the scale variation band of next to leading node calculation is shown on these plots with this shaded bands. So we clearly have some problem at high hadronic collision energy. And if you look into this next to leading computation, you realize that this problem comes from the behavior of next to leading node partonic cross-section sigma hat at high partonic collision energy, namely when this energy of collision of these two gluons or photon with gluons becomes much larger than the quarkonium mass. Then this blow up of the scale uncertainty, then it turns out that the integral is dominated at high hadronic collision energy by this high partonic collision energy region, and you get this blow up of the scale uncertainty. Fine. So we have to do something with the sigma hat at high partonic collision energy, and the formalism to solve this problem is known very well for a long time. It is the high energy factorization in leading logarithmic approximation. It resums the corrections which go like alpha s to the n times log of partonic collision energy to the power of n minus 1. And in the photo production case, the picture is like this. You have a collision of photon with gluon with very high energy s hat. And then most of this energy, actually most of the plus component of momentum, is carried away by this cascade of emissions of additional gluons, and only a very small fraction of this energy is taken by the production of our quarkonium together with one mandatory gluon to conserve color. And so this is the diagram for the partonic coefficient function. So we can refactorize it as follows, as a convolution of a resummation factor, which I call C, which describes this cascade of high energy emissions, together with the factor which I call HEF, coefficient function H, which describes this part of the process where the quarkonium is produced. And the convolution is both in terms of longitudinal momentum, which is called here y, and in terms, importantly, in terms of transverse momentum of the so-called regized gluon, which is entering into this coefficient function of high energy factorization, so the QT. And this QT dependence of both coefficient function and resummation factor is very important for this formalism. And for the Hadra production case, the picture is very similar, but now we can have two such cascades of emissions from both sides of the collision. So we have two resummation factors in the convolution times the HEF coefficient function, which depends on two transverse momenta, Qt1 and Qt2. And we know how to calculate them in the leading node in alpha S and in the leading logarithmic approximation. So where these resummation factors come from? They come from the solution of leading log BFKL equation with this collinear initial condition. And of course, since we are inclusive, we have all these additional emissions which will generate collinear divergences. So at each order of in alpha S, you get collinear divergences, which you have to subtract from this solution. And as a result, in Mellin space, after subtraction of collinear divergences, the solution acquires the dependence on this factorization scale μf. And in Mellin space, it looks really simple like this. And now I would like to emphasize that this μf dependence should really match the μf dependence of our PDFs, because otherwise we will have, because our PDFs also depend on μf, and but as you can see, for the resummation factor, it is governed by this anomalous dimension gamma, which is a solution of this equation, which is in principle a series of alpha S. But our PDFs know only about the first term of the series. So the approximation, since we want to use in our calculation the usual next to leading node PDFs, we have to truncate the series up to this leading term. And then we are essentially downgrading our approximation from full leading log approximation in terms of alpha S times the high energy log, down to double log approximation, where we take into account in our resummation factor only terms which are proportional to both the high energy log and the log of Qt over μf. So this is the approximation we will be working with. And one crucial cross-check, of course, is that if we take our resummation formula and we expand it up to next to leading node in alpha S, then we should reproduce the high energy limit of next to leading node hard scattering coefficient. And we indeed do so, and this cross-check was done both for the eta-C Hadra production and for GPSI photo production. And we can even predict the next to leading node term for the alpha S squared times the high energy logarithm in the next to leading node coefficient function, if it ever will be computed. Okay. So and now we will proceed as follows. We have two approximations for our partonic coefficient function. At high partonic center of mass energies, we want to use our resummed resultant high energy factorization. And at moderate, let's say, partonic center of mass energy, we still don't have anything better than our next to leading node fixed order result. So what we do, we glue these two contributions together using the smooth weight functions, which we build according to this inverse error weighting method, which was first introduced in this paper. But we actually we have found that one can construct these weight functions out of estimates of errors of each contribution, which can be done in a unique way by comparing it with the contribution in the opposite limit, let's say. So unfortunately, I don't have much time to discuss it in the details, but the point is that this method can really be bootstrapped and does not introduce any additional free parameters. And so then what we get is that we have our partonic coefficient function as a function of partonic center of mass energy. So for example, on this I will be showing on this plot in the bottom, which corresponds to the photo production case, which smoothly interpolates between the next to leading order result at moderate partonic center of mass energy and high energy factorization at a high partonic center of mass energy. And what it gives us, if we integrate now this result over the partonic center of mass energy, then we don't get anymore this blow up of the scale uncertainty band which we had in the fixed order calculation. So the problem is solved. Moreover, the resulting scale uncertainty band is significantly smaller than the leading order scale uncertainty band, which is gray in these plots, which is of course enormous. Okay, so this is also nice. In fact, for the photo production case, our prediction happens to lie somewhere in the ballpark of existing data, which is also nice. And in future, we may hope that, for example, ultra-peripheral collisions at the LHC can give us maybe one or more points in, let's say, hundreds of GeV region of square root of S of gamma P. So we have Kate Lynch, who is working on the feasibility for such a measurement in our group. So this concludes the first part of my talk, and I hope I still have about 5-7 minutes, right?
Right.
Can you hear me?
Yes, yes, you have 5-7 minutes. It's fine.
Yes. Okay. Thank you. So all of that is of course nice and well, but still we have a very significant scale variation uncertainty in this computation, even in the high energy region, well, especially in high energy region. So we would like to decrease it, and for this, it is necessary to go beyond this double leading logarithmic approximation, which I was discussing. And one of the elements to do this is it is really necessary to compute. The next to leading order correction to this coefficient functions of high energy factorization, which I was discussing. And this is the point of my second part of the talk. Namely, I will consider the one loop corrections to this objects. And the formalism to really compute these corrections is the high energy gauge invariant effective theory for multi-regia processes in QCD, which was introduced by Lipatov many years ago. And this effective theory includes not only the usual quarks and gluons, which are, the usual gluons here on the slide are in blue, but also the regized gluons and quarks. For these processes, we need only the regized gluons, which live in T-channel. So, for example, if you want to compute the asymptotics of scattering of scattering amplitude of two gluons to several groups of gluons, which are highly separated in rapidity. So there are large rapidity gaps between this cluster and this cluster and this cluster and the cluster at the bottom. Then at tree level in this effective theory, you will have to compute only diagrams with this structure, with exchange of two regized gluons in T-channel between these clusters, while these regized gluons are interacting with usual gluons through this non-local Lagrangian, which involves the Wilson line W, which goes along the light cone. And this Wilson line can be expanded in alpha S, and then you realize that you have a vertex of interaction of reduced gluon with the ordinary gluon, so transition vertex region to gluon, then region to 2 gluons, region to 3 gluons, and so on. So you have infinite amount of such vertices. But at finite order in alpha S, of course, you need only few of them. And if you are going to do loop calculations with this effective action, then there is a new phenomenon that you get new type of divergences which cannot be regularized in dimensional regularization, which are rapidity divergences, which are in one-to-one correspondence with high energy logarithms which we want to resum using this formalism. And okay, one of established approaches is to regulate this rapidity divergences by tilting these Wilson lines in the effective action from the light cone by a small amount. You see, I add to n plus and minus a small amount of the opposite light cone component, and R is our regularization parameter for rapidity divergences. And then, okay, just to start with something, let's calculate the one loop correction to, for example, this impact factor, region plus photon to CC bar in this one is 0 octet state. So we have we have two types of diagrams. The first one come from just the coupling of region to a gluon, which I have mentioned. So the first term in this expansion. And the second type of diagrams come from the coupling of reduced gluon with two gluons. So this is the second term here. And what I do is I take these diagrams, I contract them with the leading order diagrams for this the same impact factor, so that I get a scalar quantity in the end. And then one can recycle the usual one loop technology. So, okay, I generate this Feynman diagrams. One exception is that since we are producing quarkonium, we have to put the momenta of this charm and anti-charm quarks in the final state to be equal to the half of the quarkonium momentum. And it introduces some linear dependence between quadratic propagators, which have to be done, which have to be resolved before integration by parts reduction. After that, the integration by parts reduction for these diagrams can be done using standard tools. And another example which I will consider is the vertex region plus gluon to region plus ordinary on-shell gluon to CC bar in the 1 is 0 singlet or octet state. Yes, and okay, so these are again the same two classes of Feynman diagrams with transition vertex and with vertex region to 2 gluons or region to 3 gluons. In this case, also contributes. And okay, as I said, in these diagrams you will get rapidity divergences, which and the coefficient of this rapidity, so they will come out as the logarithm of our rapidity regulator. And the coefficient in front of it is known. It is the so-called one loop trajectory of a gluon. So we reduce these diagrams down to scalar integrals, and then there are several types of scalar integrals depending on how many usual quadratic propagators and light cone propagators you have in them. And the diagrams and integrals with one quadratic and one light cone propagator are the most singular, so they contain this kind of power law dependence on the regulator. Then these diagrams in the next diagonal, these integrals in the next diagonal are less singular, but they still contain the power law dependence r to the plus epsilon in them. So my point is that all these contributions of these red integrals have to cancel. And the only contribution, the only rapidity divergence we should be left with is the divergence proportional to the logarithm of r. Okay, but since we now have massive quark, we have one additional complication, that we have integrals which are mixing massive propagator and massive propagators and light cone denominators, linear denominators. But fortunately, this is not a big problem, because you can do the following trick. can choose this constant kappa in such a way that in one term you are left with only massless quadratic propagator and your linear denominator, but in the second term you have two quadratic propagator, but you can arrange the constant kappa in such a way that the linear denominator cancels. So you can split, the point is that you can split away the mass dependence into a piece which is just the usual one loop Feynman integral, while for this integral with linear denominator, which may contain rapidity divergences, you have to do a much simpler calculation without masses. And this is really very fortunate. So this allows me to go through with this calculation. And indeed what I found is that we are left with only single logarithm rapidity divergence, which is with the right coefficient in front of it, with the jet trajectory coefficient in front of it. And the other 1 over epsilon and 1 over epsilon squared terms also make sense, in fact. For both of these processes, for both of these impact factors, I have tried to compute, and then we can write them like this. So after we subtract the mass counter term in the on-shell scheme, and then we get the following analytic results for these two impact factors. So so Maxime, please don't throw tomatoes at me. I know that these combinations of dialogues can be simplified a lot, but I really had no time to do this. So yes, I should improve on that.
Yes, please.
Okay, so yeah,
I think you should conclude.
I'm finalizing now. So, and moreover, having this impact factor from this combination of results in the effective theory, you can assemble the high energy limit of gamma glue to CC bar plus glue amplitude in the full QCD, and the numerical comparison shows that for more precisely for the real part of it, and the numerical comparison shows that the result is indeed correct. So now I will simply move to my conclusions and simply say that there is this problem that transverse momentum integrated cross sections, or even the cross sections at small p or at PT of order of quarkonium mass in quarkonium production have perturbative instability, and this can be really solved using high energy factorization. And now we are working at continuing this solution beyond this double logarithmic approximation which I presented. And the important part of that is the calculation of corrections, one loop corrections to impact factors with quarkonia, which also, using the formalism I have described, seems to be going well. So thank you very much for your attention. Hi, hello?
Yep, yeah, so we are collecting questions now, if any.
Any question for the audience? From the audience.
I have a short question, and you didn't consider quark fragmentation in your processes. Why? Light quark fragmentation.
No, sorry, can you repeat, please?
I'm saying in your processes you didn't consider a light quark fragmentation into JPSI.
First, if we are talking about the fixed order contribution, then all next to leading order contributions are actually include quark induced and gluon induced. But for high energy contribution, the point is that only at leading power in energy, when asymptotically, when energy is much larger than any other scale, only processes with gluon exchange in T-channel contribute.
I'm speaking about a photon which is interacting with a light quark, and the light quark which emerges, emits a gluon which produces a quarkonium. And this is a
so if I come back to the very beginning, then so for example, at next to leading node for this first process, you can also have the process gluon plus quark to CC bar plus quark. And this one is included. Yes, this one is of course included, although it is a small contribution.
Okay. Yeah, this is a question?
Yes. Okay. Hi, Maxime. Nice presentation. So I would like to know if you plan to apply your formalism to transverse momentum dependence of the gypsy particle.
Sorry, there is a very strong echo. So can you repeat the question?
If you plan to apply your formalism to the PT distribution of gypsy.
Yes. So for PT distribution, it is in fact quite interesting because currently in an ArcUCD fits in collinear parton model, we have to start from values of PT like 3, 4, 5 GeV. And in fact, this region of PT, I emphasize, of order of quarkonium mass, not much smaller, but of order of quarkonium mass, is considered to be dangerous and not well described. So people rather prefer to start from something around 10 GeV. So there is only one fit of Bernd and Matthias which goes below 10 GeV, and chi-squared is not very good there. So my take on that is that in this intermediate PT regime where PT is of order of mass of the quarkonium, not much smaller, but of order, but the collision energy is very high. These high energy enhanced contributions are really important. So one have to do the similar matching calculation for the PT spectrum also. So between the next to leading node in collinear parton model and the high energy factorization. And this is more or less in progress. So we are thinking how to put it together. Yes. So stay tuned. So what I wanted to emphasize is that usually this problem is attributed to the contributions which can be resummed by TMD factorization, but really the TMD factorization is applicable if it works at all, if it factorizes at all for quarkonia, then it is applicable at PT much smaller than quarkonium mass. And we are getting the problem really at PT around the quarkonium mass or slightly bigger than that. So that's why I think that high energy enhanced contributions are important here. So thank you.
Okay, thanks, Maxime. We will have also a session about transverse momentum distribution with quarkonia later today, so we can have more seminars about this. So thanks, Maxime.
Okay, thank you.
And now we go back to usual in-person talks. Thanks.
Javier Jiménez Peña.
Okay, so I'm leaving now because there will be no broadcasting, right? To here.
Yes, there will be no broadcasting. Thank you.
Hola, probando. ¿Se me escucha? Sí, ¿no?
So, as mentioned, the next speaker is Javier Jiménez Peña. He will present measurements on the top quark mass with the Atlas experiment in 13 TeV proton-proton collision data. The floor is yours, whenever you want.
Okay, thank you everyone. I will change a bit the topic from the experimental point of view, although I will also focus at the end in the modeling aspects that are limiting the measurement. So, as an introduction, the top quark is the heaviest. Is it not working? No. Hi. Si lo cojo de mano ya está. ¿Está encendido? Sí, y no sé, el mute no está. Azul. Hola. Sí. ¿Ahora sí? Sí. Okay, so coming back to the topic, top quark is the heaviest particle we know. It has a very short lifetime, half times to 10 to the 24, and it decays before adernizing. So it's actually a unique possibility to study the free quark and its properties, like the mass, the width, also spin properties, production asymmetries. I will cover the mass in detail, but I think I will have time to cover a new measurement related to the spin if I have the time. The mass of the top quark by itself is also very interesting research as a topic because it has important implications. For example, given the large value, it has a big impact in the electroweak stability of the vacuum because the radiative correction from the top quark are the main drive of the Higgs cell couplings with negative values. And this you can observe here that the uncertainty is driven by the value of the top quark mass. And also between the top quark mass, W boson mass, and the Higgs boson mass, we can do a self-consistency test of the standard model that can be observed in this upper plot. So I will cover here direct measurements of the top quark mass. These ones target what is usually referred to the Monte Carlo generator value of the top quark mass, not the pole mass or the MSR bar, other schemes that are more clear from a theoretical point of view. But these direct measurements achieve very good precision. For example, we have several measurements reaching sub-GeV total uncertainties. One example is the latest combination of Atlas and CMS results from round 1 that was released just a month ago, reaching an uncertainty of 0.33 GeV. Or a recent measurement from CMS, our colleagues, that also reach an excellent precision of 0.38 GeV. Here we'll cover the lepton measurements using Atlas run-to data that is being shown in this plot with the red box, and you can find more details on this reference. So as an introduction, the lepton template method was the most precise measurement of Atlas 1 in round 1. Achieving a total precision of 0.4 stat and 0.74 systematic precision. The main systematic were basically related to the determination of the energy of the jets that were used for the measurements and also the data statistics. Here you can see the plot with the final measurements. We were using this reconstructed invariant mass of the lepton and the B jet. And to reduce the uncertainties, a cut in the PT of the lepton B system was used of 120 GeV, which is the situation now at 13 TeV. We have larger data set. Mainly we have 7 times the luminosity, and also given the highest energy of the collisions, we have an extra increase of the cross-section. We have improved the reconstruction of the system using a deep neural network. I will talk about that later. We have changed to use only one of the 2 lepton B-jet pairs, the ones that is better reconstructed per event, and this helps us reducing systematic uncertainties, and we have cut even harder on this transfer momenta of the lepton B-jet. The selection in a nutshell is we are using single electron or single muon triggers. We require 2 opposite sign leptons of this PT. We also require 2 big-tag jets. And we have some requirements, for example, in the invariant mass of the 2 leptons to avoid contribution from Drell-Yan or Z boson production. The most basic signature of this kind of events is that we have a top anti-top. Each is decaying to a B and a W, and the W is decaying also to a neutrino and a lepton in both sides. So one of the first things we need to do is to associate which B jet is coming from the top and which B jet is coming from the anti-top. One of the ingredients is that we could have a situation in the detector that one of these, for example, the lepton or the B jet is directly not reconstructed because it goes out of the detector phase space, and this will be a matchable one. So it doesn't matter which permutation we select, it's going to be wrong. But if we have all ingredients, we could do it correctly or incorrectly. And we can define this reconstruction efficiency, which is basically, or the signal purity, is basically the ratio of correctly match over the all kind of events. So as I said in the introduction, we have improved the reconstruction using a deep neuronal network. For that, basically, we train the DNN with events in which we use the correct permutation as a signal and incorrect or unmatchable events as background. And we use variables that depend on the permutation, like, for example, the invariant masses of the lepton and the B jet, the angular separation between them, to select to define signal and background. It works very well, improves the reconstruction efficiency when we compare to previous measurement, achieving a reconstruction efficiency close to 90%. Also, we can use the score of the DNN of the selected permutation to further increase the purity of the signal, because this small bump in the middle is due to incorrect permutations, so we can cut them away. And this also helps reducing background contamination. The event final selection, as I said in the introduction, we moved from using both pairs. We have 2 leptons, 2 jets, but we decided just to use the best reconstructed one, which is the one with the largest transfer momentum of the lepton BG system, because it has a higher reconstruction efficiency, close to, above 97%. This helps reducing the systematics that we further do with a cut, as I said before, in the score of the DNN itself, the transfer momentum of the lepton, and also on the invariant mass of the lepton BGS system that we use for the measurement itself. We see that there is a good data Monte Carlo agreement, and also the event yields, although we use only normalized distributions, is also in good agreement with data and Monte Carlo. For the measurement itself, we use the invariant mass of the lepton and the BGS system with more the highest transfer momenta. We optimize the range that we use of this distribution for performing the fit. You can see here this invariant mass, how by changing the Monte Carlo top core mass, it has changes in the shape that we can use to extract the top core mass. You can see that the highest sensitivity is in the upper tail on the right. But for example, this area is also affected by jet energy resolution effects from the detector. So we optimized the range from 50 to 140 to reduce the final uncertainty. The procedure at the end is to do an combined maximum likelihood fit to data using this distribution, and we derive templates with different values of the top core mass for TT bar and single top events. And we have such a small fraction of backgrounds, is close to 0.5%, that we assume no backgrounds. And we tested that this doesn't introduce any bias in the measurement. The final measurement is shown here. You see here the data and the fit to data. The final measurement is 172.21 with a total uncertainty of 0.80 GeV, which improves the round 1 result. The leading uncertainties, in this case, we are no longer limited by detector systematics or statistics. The statistics is only 0.20, but the biggest one, as you can see, are the matrix element matching, the recoil scheme that I will cover in detail later, or effects like correlate connections. jet energy scale is the dominant one from the detector point of view, but it's much reduced when we compare to round 1. So the situation now is that to further improve in this kind of measurements, we need to improve in signal modeling. So I will cover in the next slides a bit of the recent developments on signal modeling. And the first one I want to cover is the matching uncertainty. As you may know, probably better than myself, in Atlas we generate events by matching the hard scatter matrix element to calculations which are done now at next to leading order with Monte Carlo generators with a Parton shower generator. For example, the nominal one in Atlas currently is Powhead plus Pythia. So we can improve in orders in the matrix element by including additional radiation directly in the calculation, or if not, by Parton shower, we include this additional radiation from the Parton shower. So what was done traditionally, for example, in the measurement I just presented, is to compare assign an uncertainty by changing the generator of the matrix element, for example, comparing Powhead plus Pythia versus AMC at next to leading order plus Pythia. But this can lead to, is taking a lot of factors into account with this two-point systematic. So we plan to move to a better description that we are gonna assign an uncertainty due to the point where this matching is done. So both Powhead and Pythia handle this order of emission with the variable related to the PT of the emission called the hardness, or PT hard. And to avoid double counting, what is done is that you first do the first emission with the matrix element up to PT, and then in the phase space which is not covered, this is the space that the Parton shower takes into account. One of the problems is that the Pythia and Powhead had slightly different definitions for this hardness. So the new uncertainty will be to use different definitions, both in Powhead plus Pythia, changing, for example, PT hard 0, which is the one which is the default definition for Powhead. You can see this is the distribution in red that doesn't really describe data at a high PT of this is the lepton, the PT of the lepton, no, the PT of the subleading jet, sorry. But we can also do the matching using the PT of the Powhead emission, so this one at next to leading order. And this, as you can see here, improves the description of the data. Okay. As I said before, we were comparing two generators of a matrix element for the matching uncertainty, but we have replaced this PT hard matching, but there were other effects between, for example, AMC at next to leading order and Powhead that we will not be covering by this uncertainty. So we have additional uncertainties. For example, the top quarter line shape is different. The treatment between Powhead and AMC at next to leading order. This you can see here. Powhead is the red curve. You can see that the dotted PT hard one, which is the uncertainty I just explained before, has the same line shape. But if we look at the line shape of AMC at next to leading order, it's quite different. It's the one green. But this we can reproduce by matching Powhead plus match spin for the line shape. So we have the bright mirror followed by the reshuffling. We can do it in different ways. And this will be also a new uncertainty in the future. And finally, one thing that we have observed both in Atlas and CMS is that the PT of the top quark is slightly mismodeled. So it's thought that this model is coming from higher order predictions. So what we are proposing here is to reweight our next to leading generator to next to leading order calculation using the fixed calculation there. In various terms, for example, we reweight in the PT of the top, the PT of the TT bar system, and the mass of this TT bar system. And with this, we improve the agreement between data and Monte Carlo. You can see here the PT of the lepton from the top, how with the reweighting, sorry, the reweighting here is helping to have a better agreement between data and Monte Carlo. because the nominal one is the red, and the reweighted one is this dashed red line that falls within the uncertainty band of the data. Another effect that is new that we found that can lead to significant uncertainties in this kind of measurement of the top core mass is how you deal with the recoil of additional radiation. As I said, the matrix element handles the first hard emission of a gluon, will be this red one, and the Parton shower is taking into account secondary emissions. For example, this gluon will radiate an additional gluon. So there is a problem is this additional gluon has to recoil with something, but choosing the B, the W, or the top can lead to systematic shift in the top core mass when we do experimental measurements. Here, there are possibilities. For example, as I said, the secondary emission could recoil with the B or the W. Also, a new scheme has been proposed to recoil with the top. And following the recommendations from Peter Scans in one of these top working groups, we have included this new uncertainty, which is the recoil to top. So this gluon recoils against the top compared to the gluon radiating against the B. And currently, this is giving a big uncertainty, the second one of the dominant ones. But this will be improved in the future by implementing this a new model for the secondary emissions called Binthia that has a better description of the shower model. Other effects are, for example, the interference between TT channel, TT bar, top pair, and WT. And this is important because the final state of top pair production, and WT when there is an additional B is basically the same, is identical. So traditionally, what we have done is to produce them individually. We produce top pair by one side, single top by the other, and then we handle the interference by diagram and removal. There is also diagram subtraction as an uncertainty. But since a bit, there is a new PB4L generator next to another that targets not TT bar or WT, but the final state of two bit jets and the 4 leptons, 2 neutrinos and 2 charged leptons. And this has a better description not only of the TT bar interference, but also of off-shell effects and non-resonant production like this one here. The plan in the future is to move to use this as a nominal generator in the future. But for the time being, for example, we have evaluated how much our top core mass will shift if we do this change right now, and is below the modeling systematic at the moment. In the last 5 minutes I want to cover another analysis because it will help me to also show you some other problems from the Parton shower, which is the first measurement of quantum entanglement in top quarks. So quantum entanglement is one of the most striking properties of the quantum field theory that basically tell us that we can have objects that cannot be described individually, but we need to describe them together. So if we look to the properties of one, they have correlation with the properties of the other. And this has been measured with photons, atoms, superconductors, and this is a very interesting topic of study by itself. Recently, some recent publication proposed to use the LHC to test quantum mechanics at the highest energy server. And one of the proposals was to use top pair production because it is predicted that close to the production threshold, so at low values of MTT bar, the top quarks are predicted to be produced in an entangled state. And this we can observe experimentally through the direction of the leptons, because the leptons at the end carry information about the spin of the top and anti-top. And what we observe when they are produced close to threshold is that these two leptons are more predominantly produced in the same direction, and the correlation of the two leptons is bigger than what could be explained by a classical theory. So we need the quantum entanglement for this high level of correlation. So the two top quarks form a 2-qubit system with this spin density matrix And what is important for us now is this, the trace of the correlation matrix, because this is a sufficient, this is enough to prove the entanglement between the top and anti-top. So the sufficient condition for entanglement is that the trace of this correlation matrix is smaller than -1, or you can explain this by different ways. But from the experimental point of view, we prefer to use this T, which is the trace of the correlation matrix divided by 3, because this is, at the end of the day, the slope of the angle between the two leptons. So how is this measurement done? We have one electron and one muon of opposite sign. We avoid same flavor to avoid set contributions. We use the same sign to determine the contribution from fakes, but in the opposite sign we have different regions. One close to threshold, that we have this MTT bar close to the production threshold, and 2 validation regions. And what we do there is to measure the correlation between the spin, this angle between the two leptons, to determine the trace. So basically we will have a reconstructed value of D, this as again the angle between the two leptons. At reconstructed level, we construct a calibration curve that translates this into particle level. And if we prove that this correlation is below -1/3, we can prove that these top quarks are entangled. So, for example, one thing that has to be done is to generate samples with different values of entanglement, but this is not a parameter that we can modify in our generators. So we develop a reweighted method to do that allows us to change the level of correlation between the leptons. And this is the measurement. So entanglement has been measured observed for the first time at the LHC. Here you can see that this is the signal region close to threshold. The measured value of this D quantity, the slope of this angle between the leptons, and this is far above the entanglement limit, which is given by this line. You can observe that there is another line, which is the prediction when we use another Parton-Schauer model, and this is understood in the last slide, because depending if this matching or how the Parton-Schauer is ordered, if we use PT ordering or angular ordering, this change in the signal region quite a lot the angle between the two leptons. But no matter which of the two models we use, we can be sure that we are more than 5 sigma below the entanglement limit. And this is something that will need to be understood better in the future for future measurements. And with this, I finish the talk. So many thanks.
Thanks, Javier, for this very clear talk. Questions from the audience? I see here a question.
Yes, it's probably a very basic question. You said you measured top mass in the Monte Carlo generator scheme.
Yes.
Is there a transformation to a more physical scheme? So can you transform that to MS bar scheme?
There is no analytical transformation for sure, but there are studies that the claim is that the Monte Carlo mass that we measure is close to the pole mass at the level of 500 MeV. So it's reaching the experimental uncertainties right now.
Okay, so the uncertainty wouldn't increase by changing the scheme?
As we move to more and more precise, probably this will be need to tackle again, but we are in the level that they are at the level of the experimental precision.
And you don't get any scale dependence on the mass, or do you?
No, we don't. We have also a program of pole mass measurements. We haven't released yet a new measurement with the run-2 data, but there are in 1.1 we have for sure. But the problem there is that they are slightly less precise than the direct measurements.
Okay, thank you.
So I have a question about this entanglement and Parton showers. Maybe I missed it, but the conclusion is that the Monte Carlos do not describe this data, right? And what do you mean by better understanding of the Parton shower?
So here I'm showing red is our nominal Plauchel Batpicia, and blue is Plauchel plus Hervey 7, which is the different Parton shower model. And what we observe is that they have a part in the region that we are interested for this entanglement. They give slightly different predictions. But no matter the one you use, you will be, the measurement data proves that there is in entangled state.
Okay.
But the problem is that if you wanna, this is done at particle level basically to avoid this problem, because there at particle level, going from detector to particle level, choosing one of the models doesn't change much the result. But if you want to move to Parton level, this is when this will become a problem. So if more detailed measurements, for example, going to Parton level, that could be interesting, we'll need a better understanding of this effect.
Okay, thank you.
Other questions? I see. Here, I'm coming.
So you said that the Monte Carlo mass is close to the top quark mass, but I think that's something I will explain in my talk on Friday, but a much more precise statement is that the Monte Carlo mass is very close to the MSR mass at the scale of 1 GeV. I never see this kind of connection in any of your experimental talks. And something else I wanted to point out, when you say that you reconstruct experimentally the jet coming from the B, there must be some soft talk with some other jet, because if the B creates a jet, then the charge of this jet would be minus 1/3, and this is never going to happen. So there must be.
I mean, we reconstruct the experimentally a jet is a bunch of hadrons and collimated together.
Yeah, but they cannot come solely from the big quark, right? There must be someone escaping and taking this charge away. So is this part of your color recognition, or how do you model? Is this part of your uncertainty?
Yeah. For example, in the color recognition, this uncertainty, what tackles is, this is done from the theoretical point of view in a very toy Monte Carlo way. So we have gluon model that assumes the color is changed with gluons, but there are other models. And this is one that is covered by the color recognition. The full procedure of factorization is complex, and I think it's not fully understood. All the models that we use are very phenomenological, I would say. But what we identify as a big jet at the end is collimated particles that, for example, we differentiate from other jets because they are displaced from the interaction point of the primary interaction, because of the big jet flights before hadronizing for a while. And this is what we define as our big jet.
My point is that some of the decay products of the top must go somewhere else. Otherwise, you would have fractional charge in your jet.
Yeah, but experimentally we cannot. I mean, we are not even able to determine the charge of these jets, because it's a
but it's going to be integer, that I can tell you.
Yeah.
So let's thank Javier again. And let's move now to the last speaker of the session.
Can you hear me? Sound works? Yeah.
Can you hear me? Perfect. So the speaker is Bakar Cherchevli. Sorry if I don't pronounce it well.
It's okay.
And he will present something about automatic computation of soft anomalous dimensional matrices for heavy quark header production. The floor is yours, whenever you want.
Hello, everybody. Thanks a lot, organizers, to give me the chance to talk about this project, which is done together with Maria Vittoria Garzelli and Sven Moch at the University of Hamburg. So the primary motivation of this study was to improve the top quark related, the measurement of the top quark related observables, primarily the mass. We had already interesting talks earlier today why the top quark is important and why the mass of the top quark is important, so I'm not going to repeat these points. Yeah, here is why the mass is important, so electroweak fits and stability of the universe. You already know this. Maybe I will stop a little bit here. This is a more or less like recent status of the top quark mass measurement. It is a combined plot of the Atlas and CMS to just refresh our knowledge how the mass of the top quark is measured. There are two primary strategies. One is called a direct measurement or Monte Carlo based measurement. Basically one tries to reconstruct the decay products of the top quark, and through energy momentum conservation you recover the invariant mass of the top quark. And the second method, which is more physical, is cross-section based measurement. Experimentally one measures a cross-section of some top quark related process, and from theory we provide a prediction which ideally should have good sensitivity to the mass of the top quark, and so you can extract this mass parameter, which is exactly the mass which enters the Lagrangian, so it has a very nice physical interpretation. Here are shown the results of recent cross-section based measurements. One has studied that if you consider TT bar plus jet production, the laser is not, is not stable, but it's working. It has very good sensitivity to the mass of the top quark, and here are the results of this measurement. And you see that they are associated with quite large errors, and the current status from the theory side is that all these measurements use next to leading order plus Parton shower. So it's expected that if you improve this, then you can improve also the mass estimation. The natural step from next to leading order would be to go to next to leading order, but for TT bar plus whatever, like for 2 to 3 and beyond, this is not very easy due to two reasons. First reason is that it's difficult to calculate virtual correction because the master integrals are mostly unknown, and even if you manage to calculate it, then it's not clear how to combine different corrections, right? Virtual, real, and real. Each of them are divergent. The claim is that when you collect everything together, these singularities cancel, but because you should perform these calculations numerically, before you evaluate such functions, you need to cancel singularities. So you need some subtraction schemes, and there are multiple of them under development, but currently none of them are directly applicable to this process with hadronic initial state. So it is clear that it will take some time to achieve fully accurate NNLO precision, but meanwhile one can still do something, and namely using threshold resummation provide a better results than just next to leading order, right? We already spoke about threshold resummation. I will just quickly remind you what's the idea. Every quantity in QCD can be expanded as an alpha S series, and such expansion always relies on the fact that alpha S is small, but of course you have a problem if the coefficients are increasing with increasing power of alpha S. And this is demonstrated here. This always happens when you have two scales in your problem or even more. Typically at next to leading order already you would have like 1 over epsilon pole coming from the virtual correction, and then after phase space integration you get another pole from the real part. Poles cancel as you see, but you are left with this logarithm which for particular phase space points gets large. if you parameterize this using threshold variable, it looks like this. They appear at every order and violates the prediction power of perturbative expansions, so you should perform resummation. Now, resummation always starts with factorization. So different singularities can be factorized into different functions. There is a hard function, soft function, and jet functions. Each of them contains big logarithms, but the idea is that we can calculate them at their natural scales. We still have perturbative power, and then we evolve everything to the common scale through renormalization group equations, and this is when the resummation happens. This has been known since many years and has been applied successfully to multiple processes. The complication for TT bar plus whatever comes from the involved color structure and appearance of final state jets, which are process specific and require detailed studies. In this talk, we are going to focus on the soft part. Again, let me refresh your mind how soft radiation factorizes. For one radiation, you can see it easily. You take soft limit and you get some hard part times some iconal factor. If you have multiple radiations, then it's convenient to introduce Wilson lines, which effectively generate, if you do this kind of expansion here, power by power, they generate required soft iconal factors for you. So instead of using like this technique of the taking limits and whatever, it's way easier to consider just Wilson lines. So for your process, let's say for 2 to 3 process, the idea is that each parton legs are replaced with Wilson lines. Then you construct formally such a cross-section, and the soft function is a collinear divergent free part. The way soft function was defined, you need like these z factors to renormalize. You derive then renormalization group equation, and this is where the soft anomalous dimensions appear. If you determine somehow the soft anomalous dimension, this governs then the evolution of the soft function. Now you noticed here there are some indices. These are the color indices. Here LB and AI, and you need them because here in this factorization these are different functions, different kinematical limits of the same observable. So ideally you would remove the color, perform your kinematic study, and then introduce color in the end, but of course in QCD you cannot do this, so you need to introduce some sort of basis. And the color content of TT bar plus jet has been studied before, and the basis is parameterized as shown here. These are some color tensors. I will discuss them a little bit more later, but for now let us accept that this is a valid choice. Good, then as I said, the idea is to replace all the partons with Wilson lines, and then at one loop you just consider all possible gluon exchange between these parton legs. So here I show all the diagrams for TT bar plus jet. And then you produce tables like this. So the color part is constructed using common QCD Feynman rules, and for the kinematical part you need iconal version of Feynman rules. These are all produced automatically. Let me discuss how the color decomposition works. Before gluon exchange, you could parameterize your basis as shown on the left side. After gluon exchange, in general, the indices will change. And you have new indices, and the idea is to relate those two indices. Yeah, and this is a matrix which you produce in case of the gluon exchange between first and fifth parton. Now, if you know the answer, it's easy to check that all these relations hold. But of course, if you don't know the right-hand side, it's hard to see that C3 times F15 is exactly this kind of combination. So you need some automatic way to do this, and this is done here. So the idea is that instead of color tensors, you see that we have tensorial indices there, we project this on our basis, so you end up with scalars, and it's easy to manipulate scalars, right? You can use matrix multiplication, division, and so on. So this is the idea. It is implemented in these packages, and they perform the one-loop calculation fully automatically. So here is the result for TT bar plus jet in both partonic cross sections. I just show a couple components, and then you can go further. You can check the photo production. Again, couple examples out of this calculation, and you can go even further and calculate TT bar production in association with 10 jets, and expectedly you produce this 21 million by 21 million metrics. So you have to evaluate 10 to the 14th components, which this tool does automatically for you. Now the only thing which is not clear yet is how the color is treated, because the basis gets large and you need to somehow parameterize it. I will explain it later, but first let's talk about the loops. This was all at one loop, which I showed you, like we saw these diagrams with one gluon exchange. In principle, nothing stops you to go farther in that approach and generate all the diagrams with at two loops, right? And we have indeed this parameter L, which controls the loop count. People have done it using that diagrammatic approach. For example, in early 2000s, Kidonakis has calculated some simple processes using that approach, but nowadays, there is a better and easier way to perform soft anomalous dimension matrix calculations at higher loops, which I'm going to discuss later. First, let me convince you that the results which you are generating using these tools are indeed correct. There are a number of consistency checks which you can do. The first one would be to check the consistency of the color decomposition. The way these functions are defined, if you correctly perform the decomposition, then when you calculate such a trace, you should get back the Born level matrix element squared. And this indeed happens for all the calculations which we did. And another stronger check, which also checks the kinematical part of the soft anomalous dimension, is to examine the infrared pole structure at one loop. You can do this using these gamma matrices on one side, and independently you can produce infrared pole structure using some different approach, let's say using Catani I operators. Just to remind you, this is what Catani I operator looks like for the massless case, and if you construct such a bracket, it generates the infrared pulse for any process. So you compare this with your calculation using soft anomalous dimension matrices, and if they match, then you know that your calculation is correct. Now going at two loops. Instead of the diagrammatic approach, we can use this formula from the paper by Becher and Neubert from 2009, which can generate the pulse, which can generate soft anomalous dimension matrix at two loop for any process. I'm not going to go through details, why is this correct and so on. You can check the paper, but we can simply take it and implement in our formalisms, because we have already all routines which do the color decompositions, right? And the other factors which you see here, these are cusp anomalous dimensions, and they are known, the expansion of them are known at a sufficient level. So we ended up developing another package which we call Wilson Labs 2, and they perform calculations at two loops. And to check that it's correct, first we try to reproduce the results from this paper by Ferroli and Neubert, where they examined the two-loop infrared pole structure for TT bar process, and indeed if you run this command, you will generate the same results which you are given in this paper, and then you can go a little bit crazy again and study, let's say, TT bar production in association with tangents, and you will end up with this 21 million by 21 million metrics. But then to check it, that it's correct, it's not that easy. This is, for example, the result for TT-bar plus jet production again, and it is untested. Like how do you want to test it? The idea would be to generate again two-loop infrared structure, but to accomplish that you need hard function at one loop decomposed in the same color basis. Now for TT-bar plus jet, for TT-bar, you can calculate that by yourself, by the way, or there are many readily available results. But for TT-bar plus jet, of course, the NLO result is known, but it's not sufficient. It's not enough to have some plot from the paper. You need all the details of the calculation. And for now, we don't have this at hand. So that's why we cannot produce two-loop pole structures to compare it with something else then. But nevertheless, you can have a look at the highest poles, like epsilon to the fourth and epsilon to the third, because for that you need only Born level matrix element squared, and this can be done, but it has not been done so far. Nevertheless, here you see the appearance of this capital F2 and F1. These are new in comparison with one loop. Yeah, they come from this triple core colorators, and indeed it's expected that for TT-bar plus jets they would appear, and as you see they appear here. Now let me shortly discuss how the color basis is constructed. There are two approaches which are quite popular. The first one is so-called trace basis. They are easy to generate, but analytically the calculation is hard in this basis. I will show you why it's hard. And then there are multiplet bases, which are harder to generate, but the calculation then is easier. Now, what's the problem with trace basis? The idea is that for any process, here we consider simple gluon-gluon scattering, you just construct all the singlet exchanges between those gluons, and then you generate all possible color exchanges between gluons. So this is what it looks like diagrammatically, and analytically it's super easy to write it down. You just take 4 T generators and construct all possible traces. So you can sit down and do the same exercise for 100 jet, for example, 100 gluon. It's easy, but the problem is that even in this case, when you take 2 of these basis vectors and you examine the scalar product, it's not 0. So the basis is not orthogonal and the whole system is overdetermined. And this is a problem for large metrics, because if the matrix is non-diagonal, even at the Born level, even the calculation of the determinant analytically becomes problematic. So the better approach is to work in the multiplet basis. This relies on the decomposition of the direct product into the direct sum, right? For example, triplet times anti-triplet is decomposed as singlet plus octet, and then in the final state you have triplet times anti-triplet times octet, and this decomposition is shown here. And again, some reminder from the group theory, if these are irreducible representations, means that they are also invariant subsets. So if you take singlet or octet, no matter what kind of symmetry operation you apply, they always remain as singlet or octet. So you should match here a singlet with this singlet. You have only one possibility, and there are then 3 possibilities to match initial state octet with final state octet. So this gives you this 4-dimensional matrix, which basis, which I have shown you earlier. This is parameterized here. Now we want to automatize this, because as I showed you, we calculated top anti-top production with 10 jets, and you cannot perform this calculation by hand anymore. So the idea is to use Young diagrams. I'm not going to go through the rules of Young diagram multiplication. You can check the PDG, for example, but here it's shown the result of the anti-triplet times triplet, yeah, this is singlet and this is octet, and then the result of 2 octet multiplication. This gives you the decomposition which I have shown you earlier. And it is known, it has been known for many years, and there are some mathematical packages which do this. But there are some problems with them. First of all of these packages work for the fixed value of NC, and if you fix NC, like number of colors, to SU3, you will miss some of the combinations which are allowed for a larger NC, but not for 3, NC equals 3. And they are also super slow, so if you attempt to multiply 10 octets, it will take forever to produce results with them. So in the end, we ended up implementing our own package, which does this decomposition. It is based on Z3 theorem prover. I don't have time to go through details what it does. You can check the backup slides to get the feeling, but it is a nice way to perform this Young diagram multiplication at once, yeah? Because what a textbook tells you is to take one cell here, try to attach it in all possible combinations so that all rules are satisfied. If not, then disregard graphs and take another cell, repeat it. So it takes multiple steps to come here. And using this approach by Z3 magic, you are generating the result at once. So you insert all the cells from here to the left table at once. I'm not going to say anything more about it because it's complicated, but it works quite efficiently. And then how to construct the basis, it has been discussed in this work by Kepler and Schodel, but to our knowledge there has been no public implementation, so we ended up implementing it ourselves. Here I just show the example how would you construct, let's say, a projector for this multiplet state. First of all, you can see how it arises. If you have we start like from one gluons, and you keep adding gluons, and you are generating newer multiplet states. At some point you come here. Of course, it's not allowed because of initial state, right? In initial state, you can only have such combinations. But it becomes important later. Let's say once you reach at 10 gluon, you can produce this 27 plet out of this 343. So it's important to have a projector of that multiplet state. Again, the idea how to construct it was described in this work, and this is more or less what it looks like. So you generated 343 after you multiplied 216 by another octet. So 5 gluons are contracted in this projector, then you have 1 gluon uncontracted. Everything is then decayed into quark anti-quark pair and contracted to some Young operators, which are chosen such that their product gives you the first appearance of your desired multiplet state. But it's unavoidable to generate other multiplet states, so in the end it has to be subtracted, and the expression, analytical expression is shown here. So of course then you should repeat it for 216 and so on, but everything is automatized, and you don't need to do it by hand anymore. So in the end, we developed these packages which are here and which are openly accessible. They can perform 2-loop and 1-loop soft anomalous dimension calculation fully automatically for any 2 to n process, any number of legs. And this is a step forward towards the automatization of the threshold resummation, but even beyond the threshold resummation, this generation of color bases can be used in some Monte Carlo generators as well. So with that, I would like to thank you for your attention.
Thanks for this nice talk. We have space for 1 to very fast questions. Any questions? Seems not. So, if not, let's thank again the speaker, and let's close this session.
So now it's lunchtime. As usual, we will close the room. So if someone wants to leave things here, or otherwise you take it with you. The lunch is for people new here. Everyone pays its own lunch. We visit the canteen. If you don't like this canteen, every building around has its own canteen. So you can have a tour. And we reconvene at 2. Those 2, no? 2 p.m. Okay. I will give indication for restaurant tonight when we reconvene.